In this module, I am going to discuss about the topic errors in chemical analysis. Error and uncertainty may seem synonymous with trivial mistakes in the lab, but they are actually well defined aspects of any numerical measurement in a laboratory experiment. It is impossible to perform a chemical analysis that is totally free of errors or uncertainties. During chemical analysis, error in measurement occurs due to faulty calibration, standardization, or random variation or uncertainty in results. The error in an analytical measurement is sum total of a number of contributing errors. Measurement errors may result from incorrect measurements due to personal perceptions, such as an error in observing our reading due to parallax error or error in noting the color change in a titration. Transcription errors result from noting down errors in the record books after making the observations. Conversion and calculation errors result from treatment of observed data using statistical tools. It is impossible to perform a chemical analysis that is totally free of errors or uncertainties. Accurate results will be obtained only when a person with great skill is measuring with best instruments. But this is impossible one. Usually, the measured value of the property will never be the accurate value of the property. The difference between these two is called the error. Common personal errors occur due to some reasons. Incomplete drying of sample before weighing, material loss during transfer of precipitates, errors in transfer of solutions, parallax errors in reading the rates and pipettes, errors in making dilutions, errors in observation of color change during titrations, transcription errors. Personal errors cannot be eliminated totally, but it can be reduced through proper training and introduction of automated analysis systems. The increase in sample size and number of observations also help in reduction of such errors. Errors are mainly of three types in chemical analysis: systematic error, random error, gross error. Broadly speaking, in analytical measurements, errors fall into two categories: systematic or determinate errors, random or indeterminate errors. Determinate or systematic errors are those errors that have definite values and have some assignable cause. For every repeated measurement carried out in the same manner, these errors are consistently the same. Systematic errors usually introduce bias into the outcome of the measurement. The accuracy of the results is influenced by significant mistakes. These mistakes can also be identified and corrected because they are reproducible. Bias measures the systematic error associated with analysis. It has a negative sign if it causes results to be low and has positive sign if the results are high. Systematic errors have a definite value. One can assign the cause for the error. The analyst can measure and account for systematic error. It can be avoided. Systematic errors are unidirectional, that is, the errors will be either more or less than the accurate value. Using this property, they can be identified. Determinate errors appear due to the following factors: defective instruments, careless operation, procedural defects. There are three types of determinate errors: instrumental errors, errors of methods or methodic errors, personal or operative errors. Instrumental errors may occur using a balance which is not properly assembled. The measuring tools also have a certain amount of determinate error. Burette, pipette and volumetric flask, for instance, always deliver slightly differently from what the scale indicates. The presence of impurities in glassware also causes instrumental errors. The excessive use and the battery's low voltage electronic devices may also experience instrumental errors. The failure to accurately and often calibrate the instruments could possibly be the cause of the errors. Similar to how changing temperatures can affect numerous electronic components, errors can result from these fluctuations. Heating a platinum crucible for a longer time at high temperature causes instrumental errors. Instrumental errors can be avoided by periodic calibration of apparatus and weights. By using best instruments, instrumental errors can be eliminated. These errors may be identified by changing the instruments. At that time, the errors will also change. When the reagent employed in the analysis are contaminated, they also introduce instrumental errors. This error is called reagent error. Methodic errors are introduced by defective experimental procedures. These are common in volumetric and gravimetric analysis. Methodic errors may occur due to the solubility of precipitates in precipitating solution. The co-precipitation and post-precipitation in gravimetric analysis causes methodic errors. The decomposition or vaporization of the precipitate on heating and incomplete precipitation causes methodic errors. Side reactions during the analysis and using a improper indicator in volumetric analysis causes methodic errors. The slowness of reaction and instability of chemical species also introduce methodic errors. Personal errors are introduced by personal defects or carelessness. The sources of this error are human defects in eyes, mind, etc. For example, in colorimetric experiments, errors will be introduced by a person who is colorblind. A person with defective eyes will invariably note down the readings erroneously. Carelessness, fatigue, and improper instruction from the teacher will also introduce personal errors. The error may creep in when the precipitate is washed wrongly, the precipitate is heated to an improper temperature, the precipitate is not allowed to cool sufficiently before weighing the precipitate, the reagent is contaminated with impurities, the deliquescent chemicals are employed. Along with this, the analyst may also introduce the error by wrong calculations, wrong placement of decimals, noting wrong signs, cooking up the results. These errors can be avoided if one works properly in the laboratory. These errors are identified by the fact that they change when the measurement is repeated. Determinate errors may also be classified into another two types: constant errors, proportional errors. Constant type of determinate errors are independent of the size of the sample analyzed. When there are constant mistakes, the relative error changes as the sample size is altered, but the absolute error remains constant. For example, let us say that 0.5 milligram of precipitate is lost when washed with 200 ml of the wash liquid. Now, if we wash 500 milligram of precipitate with 200 ml of wash liquid, 0.5 milligram of precipitate will be lost. So, the loss is 0.5 into 100 divided by 500. We obtain 0.1%. Let us assume that we wash 50 milligram of the precipitate with 200 ml of wash liquid. Here also 0.5 milligram will be lost. So the loss is 0.5 into 100 divided by 50. We obtain 1%. Thus, we find that a constant error will become more serious as the size of the quantity measured decreases. So, to minimize the effect of constant error, we have to use a large sample. The magnitude of proportional errors increases or decreases in proportion to the size of the sample taken for analysis. If the impurities present in the sample is not removed, it will cause proportional errors. For instance, while estimating copper with potassium iodide, samples are contaminated with ferric ions. Iodine is also produced from potassium iodide. Thereby, error occur in the estimation of copper results. Determinate errors can often be materially reduced by a standard addition of a reagent. A known amount of the constituent being determined is added to the sample. Then the sample is analyzed for the total amount of constituent present. The difference between the analytical results for sample with and without the added constituents gives the recovery of the amount of added constituent. Determinate errors can be reduced by using internal standards. This procedure is of particular value in spectroscopic and chromatographic determinations. It involves adding a fixed amount of a reference material to a series of known concentration of the material to be determined. The ratio of the physical value of the internal standard and the series of known concentrations is plotted against the concentration values. This should give a straight line. Determinate errors can also be reduced by using amplification methods. Determination in which a very small amount of material is to be measured. This may be beyond the limits of the apparatus available. In these circumstances, if the small amount of material can be reacted in such a way that every molecule produces two or more molecules of some other measurable material, the amplification of the quantity may then be within the scope of the apparatus or methods available. From isotopic dilution method, determinate errors can be reduced. In this method, a known amount of the element being determined containing a radioactive isotope is mixed with the sample and the element is isolated in a pure form, which is weighed or otherwise determined. The radioactivity of the isolated element is measured and compared with that of the added element. The weight of the element in the sample can then be calculated. Independent method can be used to eliminate determinate errors. If the sample to be analyzed is contaminated with impurities, that is, not available in pure state, then this method can be used to minimize errors. First, the sample is analyzed in a particular method. Then, it is analyzed by a different method of established reliability. For example, hydrochloric acid is estimated volumetrically by titrating against standard sodium hydroxide. The sample hydrochloric acid is added to silver nitrate solution to obtain silver chloride precipitate. Then the precipitate is weighed and the amount of hydrochloric acid is estimated. When the amount of hydrochloric acid estimated is the same in these two methods, this serves as a correction for methodologic errors. In some instances, the accuracy of a result may be established by carrying out the analysis in an entirely different manner. Thus, iron may first be determined by gravimetrically by precipitation as ferric oxyhydroxide after removing the interfering elements, followed by ignition of the precipitate to ferric oxide. It may then be determined titrimetrically by reduction to the ferrous state and titration with a standard solution of an oxidizing agent such as potassium dichromate. In some experiments, the accuracy of a result may be established by running a parallel determination. These serve as a check on the result of a single determination and indicate only the precision of the analysis. The values obtained for constituents which are present is not too small, an amount should not vary among themselves by more than 3 parts per thousand. If larger variations are shown, the determinations must be repeated until satisfactory concordance is obtained. Let you know about how to minimize errors. Determinate errors can often be materially reduced when all instruments calibrated and the appropriate corrections applied to the original measurements. The equipments are to be calibrated periodically. This is because instrumental errors arise due to wear, corrosion, or mistreatment. In some cases, error cannot be eliminated. In such cases, we can apply a correction for the effect that it produces. For example, impurity in a weighed precipitate may be determined and its weight will be deducted. Constant errors affecting physical measurements can be frequently evaluated with a blank determination. In this, all steps of the analysis are performed without the sample. This result is then applied as a correction to the actual measurements. The object is to find out the effect of the impurities introduced through the reagents and vessels or to determine the excess of standard solution which is necessary to establish the endpoint under the conditions met within the titration of the unknown sample. A large blank correction is undesirable because the exact value becomes uncertain and the precision of the analysis is reduced. Blank determination is useful to correct errors that are due to the introduction of interfering contaminants from reagents and glassware employed in the analysis. Running a controlled determination under as nearly as possible identical experimental conditions upon a quantity of a standard substance can reduces error in measurements. Indeterminate errors are also called accidental errors. Indeterminate errors arise from uncertainties in a measurement that are unknown and which cannot be controlled by the experimentalist. When pipetting out a liquid, the speed of draining, the angle of holding the pipette, the portion at which the pipette is held would produce indeterminate errors in the volume of the liquid which is pipetted out. Indeterminate errors appear due to instrument uncertainties, method uncertainties, and personal uncertainties. It is difficult to identify indeterminate errors.